SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and the topic of our today's discussion is the regenerative principle of steam power cycles. So, today we shall briefly discuss about the regenerative principle, but before going to this, it would be important if we discuss why this regeneration is important in the context of the steam power cycle. So, if we try to recall the schematic depiction of a steam power plant, we have seen that there are 4 major components. And we have seen that all the processes can be represented or can be analyzed using the simple Rankine cycle. If we try to draw the TS diagram, so I am trying to draw the TS diagram. This is for so this is the TS diagram of the simple Rankine cycle. And what we can see that even if we go for the modification or for a modification of the simple Rankine cycle by superheating the steam beyond 0.3, and if we try to draw the TS diagram over here, so you know that this is modified Rankine cycle. what we can see from these two diagrams, that whether the plant is operated following the simple Rankine cycle or the modified Rankine cycle, the important issue is the segment at which heat is added at a lower temperature. So, if we give the name, so this is 2 prime, this point, and this is also 2 prime. So, you know that the component or sensible heating that is 2 to 2 prime, this sensible heating lowers the temperature at which heat is added to the cycle, and it is because of this factor thermal efficiency of the Rankine cycle or modified Rankine cycle becomes lesser than that of the Carnot cycle. Okay. So, idea is, if we somehow can increase the temperature at which, I mean, or if we eliminate this particular component, or if we increase the temperature at which heat is added, you know. So, in the boiler there are two components, that is sensible heat transfer, that is 2 to 2 prime, and remaining either 2 prime to 3 or 2 prime to 3 prime, depending on whether it is simple Rankine cycle or modified Rankine cycle. You know, if we can improve the heat addition at 2 to 2 prime, or if we can eliminate this part at all, I mean, if we can eliminate this low temperature heat addition inside the boiler, then efficiency of the plant can be increased. The way by which we can increase the heat addition at a higher temperature into the cycle, for which efficiency of the cycle would be higher, it is very unlikely that the efficiency would be equal to the Carnot efficiency, but attempt can be taken to increase the efficiency of the simple Rankine cycle or modified Rankine cycle, that of the Carnot cycle efficiency. So, this could be made possible by making use of the regenerative principle. So, let me repeat it. Idea was that we have understood from previous classes, what we can see even from today's discussion is that efficiency of the cycle, which is used to describe the processes in a thermal power plant, is less than that of the Carnot cycle efficiency. Attributable factor for such a decrease in efficiency is the sensible heating component, that is 2 2 prime. So, this segment, which is nothing but the heat addition at a low temperature, eventually lowers the average temperature at which heat is added to the cycle, and which in turn results in a reduction in the thermal efficiency. So, we need to find out, rather we can understand that if we can eliminate this segment, or if we can reduce the low temperature heat addition, then efficiency can be increased, though it cannot be made equal to that of the Carnot efficiency, but at least efficiency can be increased, and this could be made possible by making use of the regenerative principle. So, let me write here regenerative principle. So, this is nothing but raising of the temperature of the feed water this is nothing but the raising of temperature of the feed water leaving the pump. So, this is nothing but the raising of the temperature of feed water leaving the pump and before entering into the boiler. So, this is nothing but the regenerative principle. You know what we can do? So, try to understand, so inside this 2 to 3 that we have seen from this schematic depiction, but from 2 to 3 or 2 to 3 prime, whether it is superheated even beyond 0.3, one point is there inside the boiler, that is 2 prime. So, the state point 2, which is at the exit of the pump or inlet to the boiler, but state point 2 prime, that is inside the boiler, wherein the heating is due to sensible heat transfer. And if we can, as I have discussed, if we can eliminate this portion or reduce this portion, we can increase the efficiency. How can we make it? We can increase the temperature of feed water which is leaving the pump, but before enters into the boiler. If we can make such an arrangement, so that temperature of feed water before entering into the boiler can be increased, perhaps heat required for such a such an increment or such an increase of the temperature of the water inside the boiler, which will essentially come from the fuel combustion, can be eliminated. So, try to understand, if we can make an arrangement so that the feed water leaving the pump and before entering to the boiler can be increased up to 2 prime, but to increase the temperature, required heat should not come from the combustion of fuel. Instead, that heating can be completed through that special arrangement. One such arrangement could be, if we can allow feed water to go through the turbine following a counterflow heat exchanger arrangement, as if water is allowed to pass through the turbine and direction of water flow should be the opposite to the steam flow direction, and that water should be taken into the boiler for further heating. If we can do so, we can increase the temperature of feed water before it entering into the boiler. So, let us quickly see it, the regeneration method. Ideal regeneration. So, I mean we have boiler, what we can do, so this is 1, 2, 2 prime, 3, 4. So, this is an arrangement that we can see. Okay. So, this is the water flow direction, this is the steam flow direction. So, this is steam flow and this is water, feed water to be precise. Okay. So, this is the schematic. What we can see that feed water which is pumped, that feed water instead of taking directly into the boiler, it is now circulated through this special arrangement, and this arrangement is placed inside the turbine, and water is allowed to flow in the direction which is opposite to the direction of the steam flow, and while water is flowing through this coil, it will take certain amount of heat from the flowing steam, and that heated water will be now taken into the boiler for further heating. So, this is an arrangement that here also need to supply heat Q in, but the required heat which will essentially come from the combustion of fuel will be less than that what is needed for this particular case. So, if we consider the size of the plant is same, mass flow rate of steam per cycle is also same. So, to get equal power output, what we can see, if we compare this arrangement vis-a-vis this one, we can understand that heat which is needed to be supplied to the boiler for this particular case would be less, and we can increase the efficiency of the plant, because thermal efficiency is essentially the function of Q out and Q in that you have seen. So, this is the ideal regenerative cycle, but while I am discussing about the favorable aspects of this particular cycle, I also should discuss about the I can say demerits. You know that this is, you can understand, you have studied in heat transfer course that this is counter flow heat exchanger type. So, one stream is flowing, that is steam is flowing in the left to right direction, while pertaining to this particular arrangement, while water is flowing in the reverse direction, and while these two streams are allowed to flow in this device, because steam is having high enthalpy. So, they will exchange heat, and as a result of which water which will come out from this coil will be having high temperature. Now, issue is, so if we make such an arrangement essentially to increase the efficiency of the cycle, you can understand that again we are going to invite additional cost involved, which is rather which should be involved with the maintenance of this coil, because it is very complex geometry. So, maintenance of such an arrangement would be again difficult. So, though idea is very good that we can take certain amount of heat from one part of the cycle, and we can use that heat to heat up the working substance in another part of the cycle, that is nothing but regeneration. So, as if we are regenerating the heat to increase the efficiency of the cycle. Let me tell you once again, idea is we can reduce the Q in which will be supplied by burning fuel. So, and to do that, this is the simple arrangement, and that is also known as ideal regeneration method, but though efficiency can be increased, but at the cost of the increment of efficiency, we are going to have special arrangement, maintenance, regular maintenance as well as initial cost of such complex arrangement should be justified with the increase in efficiency before this particular arrangement is considered in practical scenario. Okay. So, what we understand from this process is that idea is to take heat from, so basically what is the working substance? Water and steam. So, idea is to take heat from one part of the cycle from the working substance, and that heat is used to supply or is used to heat up the working substance in another part of the cycle. In that way we can reduce the quantity of heat that should be supplied from the external source by burning the fuel. So, this is the concept, though this is not really feasible in practical scenario, accounting for the complex geometry of the system, we can find out several other avenues by which efficiency of the cycle can be increased. What are those? So, let us briefly discuss about the TS diagram, and we can see why such an arrangement, such a process will increase the efficiency of the cycle. Okay. So, if we try to draw the TS diagram, right, if we draw the right. So, we consider the simple Rankine cycle. Here so, this is 1, this is 2, this is 2 prime, say this is 3 and this is 4, right. Right. So, this is basically the TS diagram of the simple Rankine cycle. Now, we are trying to discuss about this ideal regeneration method by superimposing the different state points which are needed to properly describe the processes which are there in this circuit. So, this 2 to 2 prime, this 2 prime is the heating. Instead of that heating, which is, I mean, if we go back to the previous slide, this 2 to 2 prime, that heating should be done inside the boiler. Now, pertaining to this particular configuration, we can see this heating, instead of making to occur inside the boiler, this heating is done here through this arrangement, that is inside the turbine. Now, you try to understand when water temperature, so you can understand T2 prime will be greater than T2 at the cost of getting the temperature of feed water should be higher before it enters into the boiler. We need to compromise the steam temperature or steam quality as well. So, this amount of heat, that is T2 prime minus T2. So, T2 prime minus T2, this amount of heat will definitely come from the expansion of steam, rather enthalpy of the steam. So, while steam is expanding, steam temperature should drop up to this point inside the turbine itself. So, we really do not know, maybe this is 4, I am telling this is the 3 prime. So, the 3 prime state point should be inside the turbine, wherein temperature would be less than T3, but this 3 prime temperature should be even greater than T4, because depending on the location of this coil. So, what we can see that this amount of heat, that is delta T, if we would like to increase if we would like to increase the temperature of water by this delta T will come from the flowing steam, right. So, what we can assume the process is reversible. If the process is reversible, what will happen? If we take, say this is the cross section, if we take any particular section, then so that if we consider, so this is the flowing steam and this is the flowing water. So, this is water, this is steam. So, if we take any cross section, at any cross section temperature of water and temperature of steam will be equal, right, if the process is reversible. Now, if we assume that this heat addition process, rather heating up process of the feed water is reversible, and then at any cross section while water is flowing in the opposite direction to the steam flow, temperature of steam and temperature of water will be equal. If that is the case, can't we write that T2 will be equal to T3 prime and T3 prime will be equal to T2, sorry. T2 prime will be equal to T3, right. So, if we assume that the process is reversible, that at any section temperature of water and temperatures of water and steam are equal, that is T2 equal to T3 prime and T2 prime equal to T3, as if you can understand. So, this is 0.3, this is 0.3 prime, this is 2 and this is 2 prime. I am making this, I have drawn it only to make you understand that at any section, even at the inlet. So, inlet and outlet is also two different sections. So, if the process is reversible at any sections, at any section temperature of water and temperature of steam, these two temperatures will be equal, and that is what we can see. If that is the case, now in this TS plane we could not show the process 3 to 3 prime, right. So, 3 to 3 prime will be a process which we could not show in the TS place until now. So, basically 3 to 4 that process we have shown over here, that is isentropic expansion, but 3 to 3 prime again that process will be there. You can understand that process we could not show here. So, 2 to 2 prime, that is the process which is shown over here. Since these two temperatures are equal, the path followed by water for this increase in temperature should be equal to the path. So, the path which would be followed by steam for this drop in temperature will be identical to the path which is followed by this water when passing through this coil. So, the path of heating, and so basically the path followed by water for this rise in temperature is identical to the path followed by steam while leaving temperature. So, this is the, so this is 3 prime and remaining, so this is 3 prime and remaining 3 prime to 4. So, remaining 3 prime to 4 prime, so let us say it is 4 prime, will be again isentropic. Okay. So, you understand that if we try to make like this. So, what is regeneration? If we give, say this is, so if we give this is 1 prime, I am giving name. So, this is A prime, this is B, this is B prime. So, if we try to look at, though I could not draw at per scale, but the area of these two segments. So, this is right. So, if we try to draw in the next slide, so this is TS plane, so this is 1, 2, 2 prime, 3, so this is so this point is 1, this point is 1, this point is 2, this point is 2 prime, this is 3, and this 3 prime will be here. So, this is 1 prime, this is A prime, and as I told you, so this is 4, this is 4 prime, and this is B, this is B prime. So, you know that so this is 3 prime. If I hatch this portion, so this is the regeneration, right. What I have mentioned that, you know, so this is 2 to 2 prime and 3 to 3 prime. So, process 2 to 2 prime and 3 to 3 prime, rather processes are identical. If the process of heating is reversible, for reversible process of heating of feed water, right, these two processes are identical. So, basically you can see what we can write, what we have written, the temperature at any cross section of steam and water. So, these two temperatures are equal, then what we can write, entropy of water is equal to. So, basically what you can see that increase of entropy of water would be equal to the decrease in entropy of the steam. So, increase of entropy of water is equal to the decrease in entropy of steam. So, I should tell increase in entropy of water is equal to decrease in entropy of steam. That means, what we can tell that increase in entropy of water, that is ds water, that is nothing but what, S2 prime minus S2. So, S2 prime minus S2, that is ds water, like, so basically is should be equal to minus ds steam equal to S3 minus S3 prime. So, you can understand entropy of water will increase by this amount and decrease of steam will decrease by this amount. This two this decrease in entropy is equal to increase in entropy of water is equal to decrease in entropy of steam. So, what I can say, regeneration regenerative heat. So, what is regeneration? Because of the regeneration, regenerative heat equal to Q regen is nothing but the area of what, a area of 1, 2, 2 prime, 1 prime, a prime, a. So, this is basically this is the 2, 2 prime, 1. So, this is the regenerative heat, right. So, this area is equal to the area 3, 4, B prime, B, 4 prime, 3 prime. So, these two areas are equal, that we can see from the schematic, because the process 2 2 prime and process 3 2 prime are same, and also we could show that the entropy, increase in entropy of water is equal to decrease in entropy of steam. So, that these two are same. So, what we can write, so this is the, it is because of this reduction in temperature or heat we can regenerate that heat. So, this is the regenerative heat. Now, what we have written that S2 prime minus S2 equal to S3 minus S3 prime, that is what we have written from this. What is S1 prime? So, S2 prime is equal to S1 prime. So, we can write S1 prime minus S1. So, S2 equal to S1 from the TS diagram we can see. Similarly, S3 equal to S4 and S3 prime equal to S4 prime, right. So, S4 minus S4 prime. So, can't we write that S4 prime minus S1 equal to S4 minus S1 prime, right. So, you know that S4 prime, what you have written S4 prime minus S1. So, S4 prime minus S1 equal to S4 minus S1 prime. So, basically you know, if we try to see that, that is delta S. So, that is delta S, right. So, if we look at that from this TS plane, so basically you know that this is delta S and also this is delta S. That means, if we look at this TS diagram, can't we say, if we use different color, that 1 prime, 2 prime, 3 prime and 4 prime. So, this is right. Try to understand, because the ideal regenerative, so basically ideal regenerative cycle we can write here that ideal regenerative cycle, which is that, if we go back to the previous slide, so that is you know 1 2 2 prime 3 3 prime 4 prime. So, 1 2 2 prime 3 3 prime 4 prime. So, this is the ideal regenerative cycle, right. 1 2 prime 3 3 prime 4 prime. So, this is equivalent to the Carnot cycle, is equivalent to the Carnot cycle, which is that 1 prime 2 prime 3 prime and 4, 1 prime 2 prime 3 prime and 4. So, this is 1 prime 2 prime 3 prime and 4, right. So, basically why? Because you know this is delta S, S4 prime minus S1 equal to S4 minus S1 prime. So, you know, so this particular segment, this is equal to this. So, I mean try to understand. So, this is also del S, this is also del S. So, basically you can understand 1 2 2 prime 3 3 prime 4 prime, that is, since let me tell you, if I use another color, since these two areas are equal, since these two areas are equal, that is basically regenerative heating. I mean if I because if we reduce this one, so if we subtract this area from this ideal regenerative cycle and if we add this area, then you can understand 1 prime 2 prime 3 and 4 you will be getting. So, by subtracting, if we subtract this area from this ideal regenerative cycle, and if we add here, since these two are equal, we are getting new cycle, and that is the Carnot cycle. So, 1 prime, 2 prime, 3 prime and 4, that you can see 1 prime, 2 prime, 3 prime and 4, this is the Carnot cycle. So, what is conclusion? That it is because of this ideal regeneration cycle, heat is added at a constant temperature and heat is rejected at constant temperature. So, what is QH? So, you can see that QH, what is QH? Carnot cycle, and heat addition QH equal to how much? QH equal to TH into S3 minus S2 prime, TH into S3 minus S2 prime, right. So, this is the heat addition for the Carnot cycle. So, this is TH, so this is TH and this is TL, and similarly heat rejection QL equal to TL, how much? S4 minus S1 prime, right. We have written that, so this is also delta S, S3 minus S2 prime, and S4 minus S1 prime is also delta S. So, what we can conclude, that the efficiency of the ideal regenerative cycle seems to be equal of the, seems to be equal to that of the Carnot efficiency. So, ideal regenerative cycle is equivalent to the Carnot cycle, in which heat addition is at high temperature, constant temperature TH, heat rejection again is at constant temperature TL, and it is because of this regeneration, at least what we can see, we could eliminate this segment at which the heat addition to the at high temperature becomes, average temperature of heat addition becomes lower. So, regeneration we can see. So, it is by making use of this regeneration we can increase the efficiency of the cycle, and very important part is this regeneration, that we will see later that it not only improves the efficiency of the cycle, but it also provide a convenient means of deaerating the feed water. Let me tell you briefly, when this steam is taken to the condenser, I have discussed this issue that condensers are operated at a pressure which is less than atmospheric pressure. So, chances are there of leakage of air into the condenser from the ambience. So, the feed water which would be collected and again will be pumped back to the boiler will be having some air, but if we cannot deaerate the feed water. So, if we cannot remove air from the feed water, it may leads to the proper design. It should not be a proper design if we do not think about the removal of air from the feed water before it enters into the boiler, because presence of air in the feed water start what I can say initiate corrosion of the boiler pipe. So, that is again very detrimental from the perspective of the boiler operation. But this regenerative not only improves the efficiency that we have seen from today's discussion, because we could show that the ideal regenerative cycle is equivalent to the Carnot cycle, in which constant temperature heat addition is there and constant temperature heat rejection is there, but it also provide a convenient means of deaerating the feed water before it enters into the boiler. That part we will discuss in the next class. But before coming to the conclusion, let me tell you, though we could establish that the regenerative cycle efficiency is as good as Carnot cycle efficiency, but such an arrangement which we have discussed today is not a practically viable solution. So, there are several other ways by which the temperature of feed water can be increased before it enters into the boiler, and those aspects we shall discuss in the next class. So, with this I stop here today. We shall continue our discussion on this particular topic in the next class. Thank you.